You know, we plug these things in every single day and probably never give them a second thought. But have you ever actually wondered what's going on inside this little white box? It's one of the most common pieces of tech on the entire planet, and we are about to pull back the curtain and see exactly how it works.
So let's get right into it. This little thing, it's not just a plug. It's like a tiny, super efficient power plant, and its whole job is to be a translator between the wild, chaotic energy in your wall and the delicate, precise power your phone needs. We're going to break down how it pulls off this little bit of everyday magic.
Now, before we can even get to the how, we have to understand the why. We need to get a handle on the huge problem that every single phone charger is designed to solve. And it all comes down to two totally different flavors of electricity. Okay, so the power coming out of your wall socket is alternating current, or AC. That means the electricity is literally reversing its direction, flipping back and forth 60 times every second. That's great for sending power over long distances, but your phone needs direct current, or DC. That's a nice, steady, predictable flow in just one direction. Trying to charge your phone with raw AC power would be like trying to fill a glass of water from a fire hose that's whipping back and forth. You'd fry your phone. Simple as that. So, the charger has to perform this incredible four-step dance to tame that wild AC power. First, it has to get the voltage right. Then, it has to force the current to stop switching directions. After that, it needs to smooth out the flow, and finally, it has to lock in a perfectly stable voltage. Let's follow a little spark of electricity as it makes its way through this whole process.
All right, let's kick things off with stage one. This is where we take that wild two-way street of AC electricity and force every single electron to go down a one-way road. This is it. This is what the power from your wall looks like. It's a classic sine wave, right? Half the time the power is flowing forward, what we call positive, and the other half it's flowing backward, or negative. Our very first job is to get rid of that entire negative part of the journey. And the piece of equipment that does this is called a rectifier. Its entire purpose in life is to perform this amazing conversion from AC to DC. And the hero component that makes it all happen is a tiny, brilliant device called a diode.
So what is a diode? Well, think of it like a bouncer at a club for electrons. It's a one-way valve. It lets the current flow through super easily in one direction, but if that current tries to turn around and come back the other way, nope, the door slams shut. It is not allowed.
So how in the world do you build a one-way street for electricity? It's actually pretty clever. You take two different types of semiconductor material, a P-type and an N-type, and you stick them together. Right where they meet, they form what's called a PN junction. And this junction creates a special barrier that will only let electricity pass when the voltage is pushing the right way. It's an invisible electronic one-way gate.
And here's the result. By using a diode, or usually a team of 4 of them called a bridge rectifier, we've chopped off that whole negative half of the wave. Now the current is only flowing in the positive direction. But look at it. We call this pulsating DC, and it's still way too bumpy for your phone. It's like a really rough, bouncy road, and we need a smooth highway.
Okay, so that leads us to our next big challenge. How do we smooth out those peaks and valleys? We need to turn this series of humps into something that looks a lot more like a flat, stable line of power.
And the perfect tool for this job is the capacitor. A capacitor is basically a component that can store electrical energy. You can almost think of it like a tiny, tiny battery that can charge up and discharge in a blink of an eye. It's like a small water tank we're going to put next to our bumpy river of electricity. So here's the really cool part. As that pulsating DC voltage rises up to its peak, it fills the capacitor with energy. Then, just as the voltage starts to drop, the capacitor opens up and releases its stored energy back into the circuit. It perfectly fills in the gaps that would have been there between the humps. And just look at that difference. With one simple capacitor, we've taken that bumpy mess and turned it into a much smoother, much more stable voltage. It's still not perfect. You can see those little dips. We call those ripples. But wow, we are so much closer to having clean, usable power. All right, we are on the home stretch. This is the final quality control stage. We need to get rid of those last few ripples and lock the output to the exact voltage our phone needs. Not a bit more, not a bit less. This last job is handled by a circuit called a voltage regulator. Think of it as the ultimate bouncer.
Its only job is to take that slightly imperfect rippling voltage we've got now and produce a rock-solid, perfectly flat, stable output. It's the final gatekeeper. One of the coolest ways to do this is with a special kind of diode called a Zener diode. Now, unlike a regular diode, Zeners are designed to work backward. When the voltage hits a very specific level, the Zener diode basically says, okay, that's high enough, and it won't let the voltage go any higher. It acts like a voltage ceiling, effectively just shaving off any extra ripples or surges that come its way. And there it is. We did it. Rectified, filtered, and regulated. We've taken that wild AC wave from the wall socket and transformed it step by step into the clean, stable DC power that your phone can safely use to charge. It really is a little masterpiece of engineering. So we just took apart a phone charger, piece by piece. But why is this so important? Well, it's because these little components we've been talking about, they aren't just for chargers. They are the fundamental building blocks of our entire modern world. You can basically break down all of electronics into two families. You've got passive components, like the capacitor we used, that just store or resist energy. And then you have active components, like our diode and its super famous cousin, the transistor. These guys can actually control and process the flow of electricity. These are the Lego bricks that we use to build everything from your TV to a spaceship. When you boil it all down, that's all this is. That's all electronics really is. Whether you're talking about a simple phone charger or a massive supercomputer, it's just the science of telling electrons exactly where to go and what to do to make them do useful work for us. And that kind of leads us to one last, pretty mind-blowing thought. We saw how a diode works, right? It's a simple one-way gate. Now, what if you had a slightly fancier gate, one you could open and close with a tiny electrical signal? Well, that's basically a transistor. So the real question is, what could you build if you had a billion of those tiny switches on a single tiny chip? Well, the answer is you could build the brain of your smartphone. A modern microprocessor has billions of microscopic transistors, each one acting as a tiny, lightning-fast switch. By arranging them in incredibly complex patterns, we create the logic that runs our entire digital world. And it all started with the exact same simple rules of physics that we just saw at work inside this humble little phone charger.